keep talking about food. It sounds
Yeah,
good
that
to
sounds
me.
good to me. Um,
The Structural Engineers Foodie Podcast.
Super niche.
Part of why I am moderately successful in structural engineering is frankly because I have so many interests. I am fortunate to have gone to school. I did my undergrad at UC San Diego, which is one of the best programs in structural engineering in the world, and then did my master's here at Berkeley and worked really hard, did really well, started at Magnuson Clemencic, which is a internationally prominent firm up in Seattle that Magnuson Clemencic has done more work in downtown San Francisco than any other firm combined. They did the Salesforce Tower. They did the Infinity Towers. They did not do the Millennium Tower. They did the Warrior Stadium. They did the 49er Stadium, and so on and so forth. Anyways, I worked there for a year, and then another firm, Degenkolb, for a couple years. And I have friends. One of my good friends was the engineer of record for the Cal Memorial Stadium retrofit and expansion over in Berkeley, and just friends who are engineer of record for this and that and skyscrapers. And one of the things I realized is that like at 5 o'clock they go home and still they read the journal or go work on a research paper. At 5 o'clock I'm like, man, I can't wait to grill up some salmon and have a nice Pinot Noir with it, or maybe do some pasta and a little Chianti, nice little kit. It's Tuesday night. I'll just do a Chianti on Tuesday night. I don't want to do anything big, just so many interests in life,
That's great.
so if you
apparently they call it ADHD, but whatever.
if it works
It's
for
working,
you, it
man.
works.
It's working well, it seems like.
You have to leverage it. You have to, I've heard an unguarded strength is a double weakness. And at the same time, an unknown strength is, I didn't realize I had the strength of juggling many things.
So that's a good segue. So can you give us you already gave us a quick background as to your education and stuff like that and your time working. So how long have you had your own practice?
19 years as of Monday.
And so you're the founder, owner of the company. How large is the practice?
We're currently 18. We've downsized a little bit because of coronavirus. We were 21 before coronavirus, and we've worked really hard to maintain staff. Even now, we're not at full capacity, but I've been told that I have a staff-centric practice. I never knew what that meant. FTF stands for a number of things. One of them is for the family, and it's a reminder to me that I'm not working for what little glory there is for a structural engineer of an award or the tallest building or the biggest or the $1 million contract. I'm working to put food on the table for my family and not to get lost in that. And I take very seriously anyone who would dare wake up in the morning and choose to come work for me. I find that incredibly humbling when I ponder it. And so really do the best that I can to be mindful that those are not economic units sitting out there. They're human beings. They're talented people. They are smart and well trained, and they have a future and a career before them. And so we're certainly we do our best to be profitable, but the profits are not they're not the final end goal. Taking great care of people and being proud of what I do when I go to bed at night is the primary goal. So for the family team fun, foundation to finish. I'm a Christian, so it also means from the Father. It's a reminder that every good gift comes from heaven above. I've heard some other things. I'm still 100% owner of the company. One of the gentlemen that works with me that I'm interested in expanding ownership with, who's just he's been here for almost 10 years and does about 40% of our business. His last name is Favretto, and he is he's half Croatian and half Italian. He came over to America probably about a dozen years ago, and with his last name being Favretto, and he does so much fabulous work here. My latest acronym is Favretto the Fabulous is the name of the company, which is great. So I just keep making up new ones.
I'm sure he loves that when he meets clients. What does FTF stand for?
It's so funny. I was out to lunch with him with my wife. My wife is on her fourth stint with FTF. The first one I fired her. The second one she quit. The third it was mutual. We're still married, same wife. So, but she's back doing business development, which she has a background in relationship management and business development and sales. So she's doing a great job with that. But we were out to lunch, and I told him, I was telling him this kind of, hey, haha. And he goes, what? I'm sorry, I didn't hear you. And so I said it again. I said it a little louder. And he's like, I'm sorry, I still didn't hear you. And so I said it a little bit louder. And he's like, I still didn't hear you. And finally, he gave this little smirk. And Shannon was just like, oh my, he was making me say it over and over and over, louder and louder. I'm like, this is why I love the guy. And it was a lark. People don't start on their own in structural engineering 5 years out of school. So I was at Magnuson Klemensic, and I was actually working on the Seattle Mariners baseball stadium and was on site for the whole year I was up there. And then when I came back to Degenkolb, I was working construction administration. The Kaiser Geary Hospital was being retrofitted and was under construction. I was working on that, and I was doing some seismic evaluations for the GSA and a couple of other small jobs. And after 2 years, I left there and went to work for Hathaway Dinwiddie. I'd done so much CA phase work, and I felt like sitting in a computer and spreadsheets and big. It's funny because I came from the forefront of the profession, the heights of the analytical aspects of structural engineering. And I didn't have the attention span to analyze a building for 6 months at a time. Mm-hmm. So I went to the general contractor side, and after a couple of years, we were kind of winding down a job a little bit. And I felt really underutilized. My wife wanted to buy a house in San Francisco. We had a baby, and I said, I'm really sorry you married a structural engineer, not an investment banker. Structural engineers don't buy houses in San Francisco. And she said, then let's move back to Atlanta. I live in California. So I was looking at the numbers. I was doing a couple of side jobs, just like little kitchen remodels. And I was like, hey, if I build at this and was busy 30% of the time and took some time off, I'm like, that's double.
Wow.
What I'm making. Like, why not? So I started 19 years ago. I started FTF Engineering, which we started doing residential remodels. And nowadays, a residential remodel might be a $15 million project. Never having had a class in wood, never having done any engineering in wood, and never having put a set of drawings together at all.
Wow.
And I'm just like, figured out that's what you do in life, right? You just figure things out. So, 19 years by the grace of God, and and counting. I think we'll get through the end of the year, but it always feels touch and go.
We're close. You only got to survive a few more months.
Yeah.
But your office does a range of different types of projects. You're not doing just single family, right? You do all kinds of stuff.
No, only about half of our work is single family at this point, and it's again, I'm tempted to single-handedly take credit or blame for the coronavirus, because at the time, well, it would have been 2 years ago, so 17 years about this time, a little later in the year, I started. It's been a good run. The economy's been up for a long time, but we should really do one of those strategic plan things. And so we got the consultant, and we all went down to Asilomar. Well, the leadership team, about half a dozen of us, went down to Asilomar for a long weekend, and we spent 3 days developing the strategic plan. And we were going to really just figure out what's good and what we want more of, figure out maybe what's a distraction, and really hunker down and grow. 3 months later, coronavirus hit.
So you had this wonderful plan.
The plan was like, what?
Yeah.
Including moving to this new office. We went from $3,000 a month in rent to $13,000 a month in rent, plus a $7,000 a month furniture bill. So it's been really interesting. It's been really interesting. But another thing that happened during that time is I've always been working to diversify. I was captivated by structural engineering because my dad was an engineer, for one, and he did, in terms of career advice, he didn't so much give career advice as much as he just poo-pooed every other profession out there other than engineering. Doctors are just pill pushers, salespeople are just idiots, he just always was. He was kind of a negative way of framing things. So I really admired engineering. high school was a period of social development for me, but math and science were really easy. They just kind of came natural. So I was like, I'll do engineering. It's what Dad does. It seems like I have an aptitude for it. And wound up in San Diego because that's where my brother was going to be. And UC San Diego turned out to be a great school. But I didn't go into structural engineering because I wanted to do houses. I went into structural engineering. What really hooked me was in 1994 when the Northridge earthquake hit and people died. And I'm a student studying structural engineering. And, we all want to have meaning and purpose. We want our work to have meaning and purpose beyond just putting food on the table. And I saw that and it was like, what a shame that we know how to keep buildings from falling down in earthquakes. And yet when earthquakes happen, people get killed. I'm excited to dedicate my life and my career's work to structural engineering and in some small way contribute to the safety and welfare of the human condition, So the house thing, it's like after you do so many of these high-end houses, we love doing them. They're really creative. My friends who do skyscrapers have said those houses that you do are harder than our skyscrapers because our skyscraper is a floor plate 50, 60, 70 times over.
Yeah.
Like there's nothing to it. Houses, your architects are like, no, I know the wall's there up above, but we're going to do a great big media room down in the base, and then we're going to, So it's kind of like money's no object. All the floors have to be 12 inches thick. So it's fun. It's exciting. But in terms of like making the world a better place, I can only, at some point I want to do something else also.
Sure.
Whether it's more, less unaffordable, affordable, low end, whatever. We've done a range of production housing kind of stuff. We have used our San Francisco Small Business Certificate to be a junior partner with my old firm, Magnus & Klemenczyk, and we've done some really large scale stuff with them, which is fun for the crew. Our office down in San Luis Obispo does some really interesting things out at Vandenberg, rocket launch towers and foundations for launching a rocket up in space. We enjoy doing the difficult, challenging type of projects that don't have answers in the back of the book. So we've done some earth retention stuff, some excavation, shoring, deep foundation stuff, commercial, just a building, brick retrofit building or whatever. So a pretty good mix of portfolio.
That's very interesting, and I think I want to hear about what it takes to design the different structures and how different they are from your perspective. But starting on a really basic definition, so for folks who maybe don't understand this, like what does a structural engineer do in the context of the rest of a typical building project team?
Yeah, one way, when people ask me what I do for a living, I've got dozens of answers. One of them that's more specifically relevant is if you wanted to build something, whether it was a home or an office or just, whatever, you're probably going to start by talking to either a contractor or an architect. Contractor, you're going to go, hey, I want to build something. You're a contractor, you build something. The contractor is probably going to turn you on an architect pretty quickly because the first thing is like, well, what do you want to build? Well, I want to build a house. Well, how big of a house? How many bedrooms do you want? How close? I remember one of the first remodels that I did was a really big remodel. And they specifically wanted one big bathroom for the kids. They had 3 kids. And I thought, that's bizarre. Like, what are you, cheap? And one of the things I've learned in structural engineering, particularly when I worked for a general contractor for those couple of years, is keep your mouth shut. Because people do smart things for a lot of reasons. No one wakes up in the morning and goes, I want to call a structural engineer today and, design some big beams and whatever. Like, it's not structural engineering that drives the project. They wanted one bathroom for their 3 kids because they wanted their kids to have to be together. Mm-hmm. They wanted their kids to have to negotiate. And it was like, wow, that is really thoughtful. So you start with an architect, and then depending on how routine of a project you might have or how how unique or one-off or complex, that architect is going to bring in a structural engineer at some point and start, hey, we're thinking of this, we're thinking of that. I'm thinking the floor plates are 12 inches thick. You can do that. Not on that budget. We want the whole back to be blown open glass, and we want to do it in wood. Like, you're not going to do that in wood. You're going to use steel. So we really kind of come in and put the bones to it. How big does that beam need to be to span that far? How many bolts do you need in that beam to connect to that column as that column comes down? If it's a clear story, you've got that loft and the columns are actually twice as tall. How big does that column need to be? How big of a footing do you need underneath that column? What kind of soil is under that column? Maybe it's bad soil and you need a deep foundation. Maybe it's bedrock and a small little footing is going to do. So that's kind of the nuts and bolts of it. But there's a quote also that I just love that I want to pull up. Give me just a second. Yeah. And this is kind of an unattributed quote, but I love it. Structural engineering is the art of molding materials we do not wholly understand into shapes we cannot precisely analyze so as to withstand forces we cannot really assess in such a way that the community at large has no reason to suspect the extent of our ignorance.
Okay. It's very convincing.
Entirely untrue,
right.
And I think we still, in this day and age, we still have big earthquakes. The New Zealand Christchurch earthquake that was probably now on the order of half a dozen years ago, and New Zealand's got very great seismic codes, particularly in concrete design, and very similar to American. The Japanese take a very different approach to seismic resistance. They kind of go brute force. We sort of say, let's go for the reed blowing in the wind, and it'll bend, but it won't break. And they had new code-complying, properly constructed buildings that after that design level earthquake, they were tearing them down because they were so extensively damaged. And it turned out there was a particular way that these shear wall buildings, these are 15, 20, 25-story buildings in the central business district in Christchurch, there was a particular way that the base of those buildings were detailed with the rebar, concrete shear wall buildings, that did not properly account for how high the shear forces could be relative to the flexural forces, and they broke.
Wow.
There's some things that we know, and there's some things that, like, be careful. We might not know that as well as we think we know that. Yeah.
It's an interesting topic as to what you guys do and the limitations of it, because one of the things that comes up very often in our profession and what people think architects do is, we were talking about this recently, they have this assumption that architects are really good at math. And that's true. Like, most architects are decent at mathematics.
Yeah, you know it's not the case.
But it's not. But I think people think about it in more in terms of, like, we're good at engineering type of math. And I always have to explain to people, like, no. Like, I can do basic arithmetic for stuff, but the engineering side is not what we do. I don't want to be doing that because I don't have the expertise or the skill, and I don't want to be in the field saying, yeah, this seems like it'll work. I don't like that. We have engineers for doing that, and it's a very technical expertise.
As I get old, one of the fun things about getting older, sure, there's aches and pains in places that you didn't even know you had when you were young, but just seeing things more clearly. Perhaps it's wisdom. I don't know. Perhaps it's, I made that mistake a couple times. I don't want to make it again. But knowing what you don't know. And the architects that I love working with the most are the ones who do have a keen sensitivity to, this is important, I don't know it. And, hey, Randy, we're just getting started on this job. In fact, one of the projects we're working on right now, the client had bought this building it's a single family house, and it really is a brick building. And they didn't really clue into that, and it's fine. Like, this is a client who has the money that, a couple $100,000 more in a brick building retrofit, it's like a rounding error. It would be one of my goals in my practice is not like no building ever damaged in an earthquake. No, that's not going to happen. My goal is no surprised client. And if we had the opportunity to look at that building when they were in the process of purchasing it, hey, right off the front, this is a brick building. It's not a brick facade, and it's a wood frame building. It's like everything else. So just the opportunity to chime in when it's an appropriate time, as opposed to, and that's actually not that great of an example. There's other examples where it's like, hey, we just got our planning permit, we're ready to go, and you're like, do you like? There's some incongruencies in your budget and your expectations and your massing and the complexity of the foundation here and the slope. Like we've got some things to unravel and put back together, as opposed to that architect who calls and says, hey, we're developing a design to submit to planning, and we just like to bounce some ideas off of you. That kind of integrated design process is always ends up in a better, you get to your destination in a little bit more of a straight line.
Yeah, that makes total sense. And that's something that I think we're always kind of preaching or talking about. And this applies, I think, for the engineers, for everyone that's the big players that are involved. If you can at least have a conversation super early on, it doesn't necessarily mean that, let's say, the three, the architect, engineer, and contractor, are all going to be working every day together from day zero to the end. But you need to touch base at the beginning to make sure you're not, starting off down a certain path and you're veering off, and by the time you speak to them, you're there's too big of a gap, and usually it just ends up costing more money or whatever else redesigning. So that actually sort of answers the question of how you would like to see projects start for you guys. Another question would be, and this would vary on the project type, but let's say for a custom single family home, since that's a little more understandable for people, I suppose. Like, how big is your team and how involved are you through the process typically? Like, is it just touching base over once around the beginning, and then when do you become really involved, or how does that work?
Yeah. From a homeowner standpoint, we might not ever meet the homeowner.
Yeah.
And part of that depends on the architect and how much the architect is perceives a need to put us in front of the owner. Part of it depends on the owner and whether that or not they have any interest in engineering, whether or not they, there is a pervasive notion in the conscious of the general public that structural engineering is a commodity, that it's like gasoline. I might stop at this gas station and it's got a little bit nicer little market and the bathroom's a little cleaner, but the gas in the car is the same thing. But it's also 10 cents more at that station and that place over there. But the gasoline's the same thing. It's going to get me where I'm going.
Right.
If you compare what we do to our peers who charge us, if you compare what we do to the similar nice gas station with the convenient mart, and the clean bathrooms, the prices are pretty comparable. But if you compare us to someone whose fee is half, like you're getting half. I've kind of said like, well, I can draw the building for that, but I'm not going to do any engineering. And by the way, you'll still get a permit. And I'll just make everything so big that I know that it works.
Right.
And you'll spend an extra $50,000, $150,000, an extra $250,000 in construction. And it's not that I'm going to like make things skinnier. I've seen the work product of engineers whose fees are significantly lower than ours, and they also don't connect the dots. Like you have a moment frame in a retrofit that's actually not properly connected to the building.
Wow.
And it's a decorative moment frame. It's not going to do what it's supposed to do. And then there's the perception that, well, the building department is there to keep us safe. And anytime you're relying on the government to keep us safe,
Yeah.
that might not be in a good place. That might not be a good place to be. They're not. The building department has no liability. If you come back, if something happens, like, hey, you gave them a permit with that bad set of plans, and they're like, yeah, it doesn't matter. It's on the engineer. So ideally, if it's a kind of routine, well, ideally, someone wakes up in the morning and they say, I've got a lot of money and I need a tax break. What if I can hire a structural engineer and pay them a lot of money? we love providing value to our clients. In fact, I headed over here. We were talking about that. It's like the number one thing that we do is provide value to clients. Like don't redo the drawings just to meet our standards when that's going to take $3,000 or $4,000 and the work product isn't any different. You haven't made the project more valuable to the client. When a recent project, house down in Portola Valley, very close to the San Andreas Fault. In fact, the San Andreas Fault runs through the driveway. I happened to do the house next door for a very good friend of mine. Just saw him this weekend. And so when he was talking with his neighbor, who's now my client, he said, you should talk to my structural engineer, Randy. He really had an interesting take on our foundation design. So they had gotten a geotech report that was basically, and this is what a geotech should do. Here's the best thing to do. And that solution was going to cost on the order of $750,000. Before you've got anything out of the ground, we're talking $750,000 of work in the ground.
Jeez.
And I understood what they were trying to do. They've got the San Andreas Fault in the driveway. They've got liquefiable soils. The soils actually get worse the further you go down. For about 30 feet down, they finally get better. And they are, they're not a cohesive soil. So when you try to drill a hole, the hole's just going to cave in on itself. So you're going to have to drill a cased hole. So they had this great idea. It's the right answer. But I'm looking at it, and I said, so they did call me, and I said, yeah, that's not how we did Brian and Cindy's, and it's not because we didn't think of it. It's because the requirement of the building code is not that you don't have any damage to your house, not that you don't have any damage to your building in an earthquake. It's that you're alive.
Yeah.
Yeah.
And nothing has fallen down. It's not like, well, I'm alive because I wasn't there. You can be in the building and you can get out safely. So with that understanding, if you want the house that is undamaged, we did that over the hill in Portola Valley. We actually had a conversation with a client, and it was clear that this was kind of a legacy project for him, that he was an MIT trained engineer, and he really grooved on the engineering. In fact, in a short meeting, he was asking me questions that were really insightful, penetrating questions about structural engineering. It was a really fun project. But as we talked about seismic performance and the longevity of his structure, he's now like a quarter mile away from the San Andreas Fault. I had this conversation. I asked the question, what do you think happens to your building, for all this green and sustainable and off the grid and energy? What do you think happens to your building? What do you expect to happen in your building in an earthquake? And he's like, nothing. I'm like, well, we could do that, but that's not what the building code would require. Building code would require simply that you're alive. There's no consideration in the building code as to the economic viability, how long you're out of service of the building. It's just life safety. And actually, one of my colleagues from my years at Degenkolb, Evan Reese, and many others in the industry and the Structural Engineers Association of Northern California put a lot of work into this. There is a nonprofit organization called the U.S. Resiliency Council, which is similar to LEED for buildings, but it really does help the general public understand seismic safety in three parameters of, well, the blunt way of putting it is deaths, dollars, and downtime. People are going to die? Nah, people aren't going to die. Okay, what about how much the damage and what's the downtime? So the one client is like, I said, hospitals, the lights don't even flicker. Like, we can do this. It's just money. and I'm a structural engineer. I'm not your financial advisor. I'm just, here's your options. So we actually designed his house using supplemental viscous dampers. Basically, we put shock absorbers in the building
Wow.
to absorb the energy of the earthquake without damaging the building at all.
This is for a house.
This is for a house, yeah.
Wow.
Cool.
So the other guy was like, I get it, and like I don't need to spend an extra half. And part of what I was saying to him is I said, look, in this case, that was about $150,000 ad on like a $5 million build. In this case, with his soil conditions, he at some point he finally said to me, he's like, so basically I shouldn't have bought this lot, right? And I'm like, well, I'm just saying,
I was going to say.
I'm not saying you should or shouldn't have bought it, but I am saying that if you want that kind of performance, you're going to need to pour $750,000 in the ground before you get out of the ground. But part of the point was, okay, fine, it gets damaged. What?
Mm-hmm.
Do you have $50,000 in damage? Do you have $100,000 in damage? Why would you buy a $750,000 insurance policy to prevent $100,000 event?
Right.
Yeah.
Yeah.
And he was like, I think you're my structural engineer. So we went back to the geotech and said, what about having a really stiff, shallow foundation? You know, we're not going to drill 30 feet down and try and get underneath this stuff. What if we just have a really stiff, basically I mean, it's literally a mat slab. It's a raft. It's a concrete raft. And we make it stiff enough so that the building's not going to, you know, you're not going to do this. You're not going to have the building like, which tears the superstructure apart. But what you might have is this really stiff raft that just tilts.
Mm-hmm.
Well, then you just come back and jack it back up.
Mm-hmm. Mm-hmm.
So in that case, we were in before they had a conceptual design, but we were involved in the conceptual design of the foundation to get the budget brackets pulled in, and then they went through, you know, we talked with the geotech, we got them to understand what we were proposing, that it still meets code. Portola Valley happens to have, because the San Andreas Fault runs right through it, they happen to have a very stringent process to review the geotechnical reports. And so we ran it by their consultant and said, this is what we're thinking. And they're like, yeah, that sounds good. And then they went into planning, knowing that they've got this foundation solution that it's still expensive. It's $250,000, but it's not $750,000. So when you have a complicated situation like that, yeah, it's great to be involved early. We did, in that case, about $4,000 worth of conceptual design on the foundation, got them through planning, and now and that was about a year ago, now we're designing the house, and the total design fee on the house is probably another like 30 or 40,000. So it was a small, you know, relative to our overall effort, and certainly relative to the overall design effort.
Mm-hmm.
Like you said, it was a small aspect of the project, but really helped eliminate some unknowns about the construction.
Yeah, a small aspect in terms of your workload and the fees that the client's paying to you or to the designer, or whoever, but significant in the amount of money they saved, and also the literal foundation of their home was being determined. I think it's really interesting that there's different levels of engineers, and basically, you know, you're talking about how to design something intelligently in response to whatever the conditions are. Whereas I don't know, I feel like maybe most people think of engineering as being much more black and white, like it's right or it's wrong, so I can just hire an engineer and he'll do it right, and then I'm good, I don't need to worry about it. But as you pointed out, there's ways to design things that are smarter to respond to specific site conditions, or smarter to slim things down, or even for aesthetics, you know, for us.
There is, so the thing with earthquake design is that we have so little, especially in the Bay Area. In the LA area, they've had a big earthquake every 10 years. And I mean big earthquake. We haven't had a big earthquake in the Bay Area really since 1906, because even 1989 was 60 miles away, and the earthquakes have a directionality effect where, when you hear, oh, there was an earthquake and it was a magnitude 7. That tells you the amount of energy that was released, but it doesn't tell you the direction in which it was released. The 1989 earthquake was down in Santa Cruz, and it really directed most of its energy towards Santa Cruz, not back up this way towards the Bay Area. So the only damage that we saw in the Bay Area was soft soil sites, deep soft soil sites, and those got clobbered. But brick parapets on unreinforced, unbraced brick buildings didn't fall off in Chinatown. Not a single parapet fell off in Chinatown. That's not a Bay Area event. LA has had big earthquakes every 10 years. They have a little bit more of a sense that, hey, in earthquakes, like, bad stuff happens to buildings. There isn't really much else in our experience of the what mankind does in this world. Hey, I've got a 10-year-old computer. It's great. No, it's not. I've got a 30-year-old car, and it's great. I've never been in an accident. Yeah, well, I hope it stays that way, because if you get in an accident in a 30-year-old car, it's not going to go well, because we have these new things called crumple zones and airbags and anti-lock brake. like structural engineers have not been asleep at the wheel for the last 100 years. We also have been innovating, but the building code is the front page of ASCE 7. Which is what defines the remember the loads that that we can't really understand. That's ASCE 7, and it's minimum requirements. It's not best practices. So can you imagine Volvo having an ad saying, "Our new car just barely meets today's requirements for highway safety, just barely." Yeah. Not an inch more. That's what the building code is. It's not best practices. Anything less than the building code is illegal construction. And again, there's this perception out that the building code is actually best practices, because if you're selling a car, it better be. Volvo's going, this is the safest car on the road. It meets the safety requirements of 2035. We're already there. Right.
Interesting.
So having that conversation, starting with the architects, because because your client, you're going to get to know your clients a lot better than I am, and this may be relevant. It may not be relevant. It may be worth a conversation. I've had the conversation where I'm doing a retrofit on an apartment building that was mandated by the city, and so this owner's kind of like, I guess I got to do it. And I'm like, well, it is a good thing. Like, your building's probably going to have significant damage in an earthquake, and I understand it's investment for you, but if you're not collecting rent after an earthquake, like, this is sort of a cheap insurance policy on that. And by the way, it makes San Francisco a better place in terms of economic recovery, the resiliency aspect of things. And he was like, yeah, I don't really care. I got a house in Montana, I got a house in Palm Springs. Okay. The building code is there, and that's what I have to do in terms of my licensure, and in terms of what we love to do is, like I said, no surprise clients. So if that guy calls me after a big earthquake and says, hey, I've got a red tag and I got to vacate the building, I'm like, yeah, that's what we talked about.
Let me pull up that email. Yeah. So let me ask you then, well, I have two questions. The first question is, how much more challenging is it to build in a place where earthquakes are an issue, like San Francisco or Los Angeles, versus not?
Total game changer.
Different, right?
Total game changer. Absolutely.
And that's because of the lateral forces, right, that happen with an earthquake. This is going back to whatever structural engineering courses I have, dealing with forces that come from the side, essentially.
Well, and not only that, because everywhere else in the world, you still have wind on a taller building. You still have significant wind design. But with the wind design, we take the wind pressures that we actually think are going to be imparted on this building, and we design for those. With seismic, depending on the system, we might take the earthquake forces that we think are going to happen on the building and divide them by 8.
Divide them by 8?
divide them by 8, and then design the building. Because it's the crumple zones. We're going to damage the building, but we're going to damage it in such a way that the occupants are safe.
Right.
So a steel moment frame building is a building where we rigidly connect the beams and the columns so that when you push on the building, they're rigidly connected. There's still some flexibility, but it's not like where they're pinned and you can just push it right over, right? It's like, you got to bend the steel and all that. Well, in the 1994 Northridge earthquake, the design and construction practices of steel moment frame construction had gone from tests on little W8 moment frame connections over at UC Berkeley to W14 by 750 columns and W36 by 450 beams. Massive. And what they found is very, very intricate, and this is back to that quote that I gave, because of a very intricate detail in the way that those welds were placed, particularly on the bottom flange, that there was this inherent crack. It's the way they did it. And that crack propagated up into the column. And it was really shocking the way that these things failed. Fortunately, the shear tab, nothing actually collapsed, but they had cracks going through these columns that were so far that it was like, this was close, and that wasn't that big of an earthquake. And again, in 1994, if you look at the LA basin, I got to turn around and look at it with you. If you look at the LA basin, Northridge is here, and the energy went up into the San Gabriel Mountains. If you look at the ground shaking intensity maps from the Northridge earthquake, you'll see the San Gabriel Mountains are like blood red, and yet Northridge and the LA area is like orange and yellow. And still, we had this kind of damage to moment frame buildings because the research hadn't really kept up with the practice. So we learned how to do that and learned how to keep those cracks from happening and really keep the crumple zones where we want them to be in the beam. Because if you yield the beam, you already have a very redundant structure with a moment frame. If you yield the beam and create a plastic hinge in the middle of an earthquake, it's not going to fall down.
Right.
It's going to absorb the energy.
Some quick things like people listening might not know. What does yield the beam mean? Yeah. And when you say like W36, you tell people how big that is.
Thank you. Yeah. So when we talk about wide flange beams or I-beams in the common vernacular, in the engineering specification for them is a W for wide flange, and then a number which is nominally the depth in inches, and then another number which is the weight of the beam per foot. So a W14 is very commonly used for columns, and a W14 by 750 is a column that weighs 750 pounds per linear foot. So the flanges on a W14 are going to be about 3 inches thick. It's massive.
Yeah, we're talking about massive. I want to make sure people understand we're not talking about
the first time that I saw a W14 by 750 was up at the baseball stadium in Seattle, and they were building. There's about a 650 foot span roof structure on the Seattle Mariners baseball stadium, and it moves. Sunny day, pull it back. Rainy day, put it over the field, and that truss that spans all the way over the field is a truss, as you would expect of that long of a span. And the truss has a single bottom cord and 2 top cords. And the truss is about 20 feet deep. And just the bottom cord is W14 by 750. Massive. It's massive. Yeah. Yeah. And these are like skyscraper type of things. These aren't, this is residential construction. But the earthquake stuff. So we're working with fictitious forces. And the goal is that there's so many checks in the building code that we can't screw it up. It doesn't get screwed up often, but the firm that I worked at, both Magnuson Klemensic and Degenkolb, which are, again, forefront engineering firms, and there's others out there. They're not the only two by any means. There's a number of them in the Bay Area. You really learn how to design a building. You're going to do math, even in grad school. I look back on my education, formal education, and it's like I learned how to do math on buildings, and it took another half a dozen years to really learn how to engineer a building, a system where you're taking the whole thing into account, and you're not just following the recipe. You're also like, I get it. I get the bigger picture. I was at Degenkolb early one morning. I like to go in early and kind of get into my work and not be too distracted. And one of the senior principals there would stop by and chat with me. And we were talking about a building that I was doing a seismic evaluation on. And I said, I don't think it's any good. I think it'll collapse. Because I'm just checking the numbers, right? No good, no good, no good. I don't think it's any good. I think it'll collapse. And he says to me, Randy, how does that building get on the ground in an earthquake? And I thought, what? What do you, the numbers, man, the numbers, the math, it's the math. And he's like, how does that building get on the ground in an earthquake? And I sat back and I was like, this building's not going to fall down. He's like, those buildings never fall down. That kind of building doesn't fall down in an earthquake. You're right. All the numbers are wrong. But that's not the building that collapsed. That's not a problem that's going to make this thing collapse. So where are those critical details in the building? Going back to this, to the quote, where are those critical details where if you get this wrong, all bets are off? Now, if I missize if I get my seismic forces wrong by 20%, well, we've already divided by 8.
Right.
If I get everything else right, it's probably going to be okay.
Right. Is one of the big differences between, let's say, a junior engineer or someone who just graduated versus a senior one? You were talking about that kind of difference for you from going from grad school to practicing. Is it also the ability to start to think more creatively in the process?
Yep. I remember another conversation that I had with a real good friend who had a similar practice as mine, but he's probably 15 to 20 years older than I am. And we were talking about our work and we were talking about something, and he said, Randy, calculations should only be used to confirm engineering judgment. What? You calculate something to figure out what he said, no. He said, you shouldn't ever be calculating something that you don't already have a sense of what the answer is. And I'm like, these old guys, they're always just killing me. And as my career has gone by, I remember, again, back at Degenkolb, I was working with a guy who was the former CEO, and he was like as old as the furniture. And he came in every day in a really nice suit, a bow tie, and he had the cufflinks, a big smile, a briefcase. And he just was so just fun to work with. And I had done days and days and days of calculations, and I was going to meet with him to go over my calcs. And he leans back in the chair, and he just kind of looks from across the table, and he pulls out his slide rule. He's like, oh, it looks like it's about 25 foot. And is that a 6-inch slab? Okay. And he's moving it, and he's like, looks like it ought to be, hand me that AISC book right there. And it's from like 1924. And I'm like, that's not going to have the right, it ought to be a W8 by 24. And I'm like, well, Tom, after 6 days of analysis and using the current AISC, it's actually a W8 by 26. They don't call them 24s anymore, but you're exactly right.
That's amazing.
Yeah. So there really does become a sense of, and architects will get that too. It's like, hey, we've done 10 of these now. You're going to have an 8-inch slab, right? Yeah. You're going to have this and that. Like you start to develop expectations, but hey, when you double the span, call me. Let's double check that or whatever. But there is really an over-reliance on the math, on the software, on the spreadsheets, and not really understanding what's the implication of this math. because it's not just math.
Right.
What are the implications of this math?
Is that because of the liability that comes with your profession?
I think it's because of the type of, the strengths of the person who goes into structural engineering. It's math, right?
Mm.
And all of us at some point in our lives, in our careers, whether it's a technical career or not, you start to get the meta narrative, the meta knowledge.
Mm.
And you can look at a movie or a series of movies, and there's a story and there's a subplot and another subplot and another subplot, but at some point you step back and it's like, what's the big story here?
Interesting.
And there's the numbers and doing the calculations. That's how we're raised as engineers, is doing math. So it's like our security blanket. It's like, I don't know, but I can go crunch numbers.
Mm-hmm.
Yeah. Yeah.
Mm-hmm.
And there's something to be said. There is a time for that.
Yeah.
But there's also stepping back and looking at the answer, going, that doesn't depend. Oh, look, I've got it in feet, not inches. I fix that. And having that sensibility, and so it's interesting. Our licensing, you're allowed to take your PE license after just a couple years of practice, and your SE license after only 5 years of experience. But really, I think most people in the profession would say it takes 10 years of practice to really start to understand how to put a building together.
Yeah.
Because of that meta visualization capabilities that you were talking about.
Yep.
Yeah.
So, in California, we don't need to hire architects on certain size of project, right? Like depending on square footage, height of stories and stuff like that. Is there a similar thing for a structural engineer? Like, can you just kind of wing it with a contractor for certain types of projects, or should you technically,
there are conventional framing prescriptive requirements in the building code, but they're very, very restrictive. It's like every room, the biggest room you can have is like 10 by 10. I would be surprised if anybody uses them anymore.
Mm-hmm. Mm-hmm.
If nothing else, the architecture, the design drives you out of the prescriptive requirements to at least having a structural engineer. When people think they're going to save by not hiring an architect, I'm sort of like, save what? Like, just because a contractor can build things and I can do math, why would you not want someone at the table who has studied and practiced proportion and theme and variation? The concept of theme and variation is really fascinating in the way that it shows up in food, in fashion, and in architecture. And music. If you want a building, as I understand it now after 25 years of working with some really great architects, and you walk into a space or you stand across the street and you look at a building and you're like, wow, something about that is wow. Mm-hmm. And it's been having those experiences with an architect when they say, do you want to know what that is? And I'm like, yes. Well, here's what it is. You see that line? You see that detail? See how that detail is there and there and there and there. So that kind of ties it together, but yet we have this variation of this and that. Because if you have a perfectly symmetrical building, it's boring.
Yeah.
But if you have a building that's just totally freeform, modern art, fortunately, is not going to come into the built environment. Frank Gehry can do whatever he does, but behind that is a rational structure.
Yeah, right.
We're not going to deconstruct building a building like we can with art or like we can with music. But that music that really inspires us, that art that really inspires us, theme and variation, and then balance and proportion. I remember going into a house and being really impressed, and the architects were really frustrated because they weren't carried through construction. They just worked with the contractor. And I was like, well, what is it? This is beautiful. I mean, look at that marble, look at that granite, look at that oak, and they're like, exactly. It's like a showroom in here. I'm like, but that's beautiful granite and like, exactly. It looks like a showroom. Like, what is the consistent, like, where's the common thread as you walk through this house that makes it not feel like a showroom, but makes it feel like the intelligence of a designer that carried that thought. Is the kitchen different from the bedroom? Of course it is, but there's also something that ties it together. Oh, maybe you shouldn't work with your contractor to design, to pick the finishes. Maybe you really should work with an architect. If you want to have that real aha moment, then keep working with the architect.
That's a fantastic point, and that's something that we're always trying to preach. So I'm very glad to hear it from you.
And it's not because you've been to Home Depot for the last 10 years. Like, you studied the science and the art of that, and practiced the art and science of that. It's not like, well, I can go to Home Depot and pick out stuff. Well, God, so can I.
Right.
And it's not pretty. My poor wife, she wanted to buy a new couch, and I'm like, I can't buy a new couch. I mean, not because I can't afford it because I'm a structural engineer, but I was like, I can't buy a new couch unless I know what the whole living room's going to do. And she's like, can we just get a new couch? The cat has scratched the leg. It's embarrassing. It's like kind of big and clunky. It's from the old place. We could get one that's little. And I'm like, just please bear with me. And in this case, I worked with an interior designer, very, very good local interior designer. And she was gracious enough to come to my home out in the Outer Sunset. She's over in Pack Heights and in Atherton and Hillsborough doing these. She gets flown to Montana to pick out stuff for the vacation home kind of thing. Mm-hmm. And we kind of looked at the room. We tore out the fireplace. We built a built-in, and the built-in theme and variation. The TV in this built-in was centered on the room, but the room had a door. And so the cabinet seemed offset, but the TV was actually on the center line, and it was just this awesome expression of theme and variation. It felt a little chaotic, but yet everything was actually lined up on the center of the room. So when you sat down on the couch and looked at the TV, it's like everything's centered and there's harmony, but yet there's variation. So we tore out the fireplace that was kind of catty corner and really broke up the room, and then just got a couple couches and a coffee table and a little fold-up table behind one of the couches because the room was a little longer than and when we were done, friends would come over and they're like, you got new furniture, but there was that kind of moment because it was all harmonized to the room. And Shannon was like, it was kind of tough waiting a year and a half to get a couch. But I get it. I see why you wouldn't just buy a couch. And I still don't know how. I still wouldn't dare claim to know how to do that. I know who you should call, and it's an architect. It's not. I can't do it.
I mean, that's the magic of design. I think you actually described it very well. And one of the big differences, more in the design discussion of things, is the differences between looking at something, whether it be a material, a couch, or a wall, as a standalone item and critiquing that and saying, I like that, versus how's it going to fit within the entire space or the entire home or the entire property it's a part of. That's kind of a different ballgame. And it's not dissimilar to what we were talking about before with what you guys do, right? There's a larger vision of the thing that has to have some kind of intelligence behind it.
Yep.
So let me ask you, with, you were talking about earthquakes and stuff, a couple key questions that I think people would be interested to know about. You had mentioned a crumple zone in buildings. And you were just saying that that's basically where the building is designed, so if it should fail, it fails there, not elsewhere. So are we talking about, I'm now speaking as a client, are we talking about like rooms that are going to collapse while others are standing up, or what does a crumple zone mean?
No, very good question. And I'll also go back, there was a question you asked earlier that I didn't quite get to. If what we're doing with earthquake design, when we take those earthquake forces and divide by 8, or 6 or 2, depending on the system, if you think about a glass rod, if I take a glass rod, I can bend it, and then it just shatters. Yeah. Right? But if I take a coat hanger, I can bend it, and bend it, and bend it, and bend it, and bend it, bend it, bend it, we can design like the glass rod, but it's going to be, and that frankly, that's the Japanese philosophy behind earthquake design. Is let's just make it so big that it doesn't yield. Or the other thing that's really popular in Japan that for some reason hasn't caught on here, even though it's a really great way to deal with earthquake forces, is either base isolation or supplemental damping, basically shock absorbers. So either decouple the building from the ground shaking, which a lot of Japanese buildings do. In fact, it's common in home construction.
Wow.
I'm still wanting to do, I've done 2 houses now that have damping. I haven't done one yet that's got base isolators. Stanford has done some research. They'll have these base isolators. City Hall in San Francisco is on base isolation. If you're walking up the steps of City Hall, look really carefully at that first step. It's actually hanging over the sidewalk so it can move back and forth in an earthquake. And there's a literal moat around. They don't put water and crocodiles in it, but there's a gap around the whole building so that the building can shake. So we want that bend but don't break. And I was actually involved in going back to the moment frames. We were involved in repairing a house that had just been built, and they started finding problems. We found more and more problems. Finally, there was a big lawsuit, and I was in a deposition, and I was explaining this philosophy. And I brought a pair of wire snips, and I brought a coat hanger, and I took one coat hanger, and I said, let's count. Because I was proving the point about those cracks in the moment frames from Northridge that caused this fracture. And I sat there bending it back and forth until it broke, and we counted, and it was like 37 cycles before it finally broke. And then I took the wire snips and I put as small of a crimp in the coat hanger as I could, just the smallest little nick. 1, 2, 3, 4, 5 broken. I said that's why that's important.
And every one of those flexes is a sway in an earthquake.
When we do the welds that don't have an inherent crack in them, then we get the 37 cycles. When we do the weld with that inherent crack, we get 3 cycles and it's gone. So the crumple zones, like in a wood frame building, you might have a lot of plywood shear walls. When the building from like your typical 10 foot floor to floor ceiling, just for easy numbers, when the floor above moves about 1 inch to 1.5 inches relative to the floor below, at that point you're going to start cracking architectural finishes. We're allowed to go 3 to 4 inches
for life safety.
So we're going to crack and damage your architectural finishes. They're going to help absorb some of the energy. What's going on behind that is a plywood shear wall, which is, wood studs and wood posts at the ends and a bunch of nails. The nails are wrenching back and forth and digging into that plywood and damaging the plywood. And after an earthquake, can it go through another earthquake? Sure. Can it go through another one and another one and another one? No. We've got 15 cycles into the coat hanger. Go through another one? Yeah. We'll go through at some point we're fatiguing. But the goal is that, one earthquake, absolutely, we've got that covered. But it is damaged in accordance with the building code.
So from that, and I know this would vary on the situations, and the size of the earthquake, but so like how resilient is a building designed to be when it comes to earthquakes, that it survives one just fine, but then after that one, would people typically have to have an engineer, what do you call it, forensics come in and like figure out what's going on?
Yeah, it's another really good question. So conventional home construction it's really light. So the forces imparted on a building in an earthquake are proportional to the weight of the building. Good old Newtonian physics, force equals mass times acceleration. The earthquake is the acceleration. The building itself is the mass, which results in a force pushing your building back and forth. it's going to be damaged. But wood frame buildings are light, they're flexible, it's sort of like they're going to be okay. It's more these, and they're also they tend to be fairly redundant, which there actually is a redundancy factor in the building code where when you don't have enough redundancy, they just make you jack up the seismic forces by 30%. There's also an importance factor. Normal buildings are an importance factor of 1 if you have either a lot of people, or you have hazardous materials, or you have a fire police station or a school, or you have a hospital. The I factor might be 1.25, it might be 1.5. But the USGS gives us maps that define the ground shaking at that site. A geotechnical engineer gives us modifiers on those numbers. In the Bay Area, we are not looking at the biggest earthquake that could possibly happen. We're actually looking at the biggest earthquake that's likely to happen. And the difference in that is we are looking at a magnitude 8.5, like just to break down the science, a magnitude 8.5 on the San Andreas Fault, with the fault rupture propagation in both directions. It's basically like a cannon with both ends open. And by the way, San Francisco is perpendicular generally. San Francisco, if you're down south, you might be along the San Andreas Fault. In, 89, in 99, in 19, I guess it must have been 2004, 15, maybe it was 2009. Yeah, it was 89. Yeah, 2009, 20-year anniversary of the Loma Prieta earthquake. Was at a symposium here, and a really, really, really smart woman, scientist, was giving just this talk. And she said, this is what it's predicated on. What happens if we have a magnitude 8 earthquake centered with an epicenter up in Point Reyes, and the cannon, basically when you have an earthquake, the epicenter is where the fault rupture starts. And the fault rupture, the zipper can go in one direction, or the zipper can go in 2 directions. And that's the direction that the energy is flung. The magnitude is just the total energy. What you care about is what happened and what was the ground shaking intensity on your site. So magnitude 8, where the cannon went off right behind you but was shooting the other way, who cares? Well, it's still a big earthquake, but a magnitude 8, just turn that cannon around, it's going to blow your head off. Her point was, what the USGS does not and will not consider is a magnitude 8 earthquake, epicenter at Point Reyes Station, and just unilateral fault rupture propagation. And the whole room, I'm sitting there like, trying to keep my nose above water to understand it. A lot of people in the room smarter than me just went, like, they knew instantly that would be a lot worse. We don't consider that in the building code. Not only do we not consider that, we take the probable earthquake where it goes both ways. And by the way, that would potentially be a 1 in 2,500 year event.
Yeah. Sure.
So to some extent, like, do you design every building for an airplane to fly into it?
Yeah.
Right.
We're still not, even though it happened.
Yeah.
We're still not doing that, even though it happened. We accept that there's hazards to, I remember reading in the newspaper one morning, some guy sitting in his living room in Florida, sinkhole, boom, he's dead. I'm like, wow, I can't even stay home and be safe anymore. So Don't get freaked out by this stuff, but we take that probable earthquake, the maximum probable earthquake from the USGS, we actually divide it by 2/3. We reduce it, and then we design for life safety.
Interesting.
So a hospital actually designs for, that's why the importance factor for hospitals 1.5 is if you multiply 2/3 by 1.5, we're right back to 1. And then they design for not even immediate occupancy, which means you can get in the building. They design it for fully functional. The lights don't even flicker.
Right.
So the idea, and this is why hospital construction in California is insanely expensive, is because, like, when you're there, when I'm there, when mom's there, and she's on the machine, there's not even a hiccup in the power supply.
Yeah. Yeah.
And everything keeps going.
So do you think that most of the projects, and this would vary by project type, should be engineered to surpass what the building code requires?
No. I just prefer that my clients know what they're getting.
It's interesting that you bring all of this up because it's a question of like, where do you draw that line? Like you were saying, if you plan for everything, well, then you're going to live in a bunker underneath the earth, and you got to dial it back at some point. To
there's
live.
100%. There's 100% probability of dying. So the goal isn't, it's like, okay, I'm going to do all that, and by the way, I'm going to go get in my car and drive to the office. Yeah, well, I'm going to, like, really? That's crazy dangerous. So yeah, it isn't to say let's eliminate all risks. That's a fool's errand. But just being the gentleman who and down in Portola Valley, he and his wife had a vision, and for the delta of $150,000, they were like, why? He's an engineer. It's like, geez, I got this car, and I love bragging about this in the car, and I've got that, and like, why wouldn't I want to do the extra? So why isn't that conversation, particularly in Silicon Valley, where a lot of this wealth is coming from, an engineering type of, engineering is so exalted in the Valley, and yet, like, how many people? I remember another good friend of mine. Again, my dad steered me to the wrong branch of engineering. Another buddy studied economics at Rice and then got his master's in economics at Harvard, and then worked for McKinsey for a few years, and then got his MBA at Stanford. I didn't even know what an MBA was until I met all these guys in my late 20s. I'm like, what's an MBA? Anyways, they all had one. So I helped him build a house down in Atherton. He retired to celebrate his 40th birthday, and we did a nice conservative structural standpoint. The architecture was what it was, but we did a nice sturdy design on that thing. And he calls me up a couple of years later, and he goes, "Hey, what's the I factor on my building?" And I'm like, "Mike, why the hell are you asking me what the I factor is?" And he goes, "Well, I was at a party." And I'm like, they've got to make a movie about that. This should have been in the Silicon Valley. What was the Facebook movie?
Oh,
this could have
Social
been a
Network.
So this should have been a scene in the Social Network movie, like, bunch of guys standing around talking about their mansions. Well, what's your I factor for the earthquake? Oh, mine's I did mine at 2. I did mine at 2. That was the cocktail party. What was your I factor on your house when you designed it for Seismic? And I'm like, well, Mike, I understand what they're asking. And we didn't exactly we just did a nice. And I'm like, let me go back and check. And I'm like, basically, so I got back to them. I'm like, basically, it's like an I of 1.25. It's like a school or a fire station or a police station. It's like it's pretty sturdy.
It's pretty robust.
After the fact, they're having these conversations. And by the way, the I factor is a really brute force way of solving the problem. In 1971 Sylmar earthquake, the Olive View Hospital pancaked.
Wow.
Soft story. It pancaked. It took decades to rebuild that hospital. Decades. They rebuilt it, and they rebuilt it to modern seismic standards, really robust. And the 1994 Northridge earthquake came along, and TVs were flying across the room.
Wow.
And pipes were breaking, and I'm not sure if they tore it down again or if they basically had to gut it and rebuild it. So the structural engineers were like, we're good. No, they had to vacate the hospital because of the non-structural components. So if I, as a structural engineer, you want me to protect a lot more than just the structure. And that's all the I factor does for you is, hey, now you're not going to have any damage in that plywood. And this is why we did, when we've done this, we do the damping. Because if I just make it stiffer and stiffer and stiffer, I'm actually driving the accelerations higher and higher and higher. It's basically like going down the road in a sports car
with no shocks.
Like, this performs really great. Like, yeah. When I throw this thing into a corner, I can pull 1.2 Gs. Yeah, but every little bump is knocking my fillings loose. That's because of the way the physics work in the equation of motion. we want to decouple the strength and the stiffness is our displacement, our accelerations. We need to decouple those, and that's why we did the damping. So careful to just like, hey, design for higher seismic force is great. Now we're just going to get more non-structural damage.
Yeah,
we haven't necessarily solved, and that's why the USRC has really done in the work that the Structural Engineers Association of Northern California did, that USRC built on. It's a great, just a simple system where you're looking at 3 areas of performance. You're looking at how much damage, and they're going to take the whole building into account. Not just, hey, your columns behind all your broken finishes and your TVs that went flying across the room, your structure's fine. Great, I still got to rebuild my building. Well, you won't have to do any structural repairs. So the cost of repairs and how long it's going to be, how long you're going to be out of that building. And that's just, just like anything else. I'm a little bit of a car guy. I don't have the money to be like a big car guy, but I love the Mercedes-Benz E63S wagon because it's a station wagon that's got one of the fastest Nürburgring lap times out there in a production car because it's got 600 horsepower.
Oh gosh!
Well,
really...
it's also $150,000, so I don't have one. Would I like to? Would that be the pinnacle of automotive engineering and performance? And by the way, no, honey, I'll get them from soccer. I thought you had the Ferrari. No, I have the car that'll go faster than the Ferrari. But no, I've got the wagon. It's like it's the engineers. It's like that's the right. We're
That's the
Toyota
engineer's
Corolla,
dream car.
Sure. Yeah, Toyota Corolla, sure. It fits the job. In fact, ironically, that same friend, he retired to celebrate his 40th birthday. Super nice guy. In fact, his sense of humor is just, it's like you laugh at his jokes 5 minutes later because it takes you that long.
Oh,
now I get anyhow, his wife is a doctor medical doctor over at Stanford. She does studies on aging and stuff, just a delightful couple. And, it took he and his wife a long time to find that lot and to decide on what kind of house to build and how to site it. And they designed it and they built it. And it's like 3-4 years later, he's been living in a rental that he's finally moving in. And he's going to move in. He's like, I got a note from my real estate agent. I guess I could sell this thing for like $25 million now. And I don't know, I'm kind of tempted to just get another rental. Like, Mike, you will be divorced real quick. You don't move in. We can't all afford that, whatever, but we can do good engineering and it really doesn't have to cost. This might sound like gold plating things, but the structure of a building typically costs about 20% of the total construction costs. Now, if you're doing, particularly in high-end residential, that number can get out of hand because when you go from $1,000 to $1,500 a square foot, that's not because of more structure. That's because you're importing your limestone from France, not a local quarry. You're buying the most premium fixtures. You're automating all kinds of stuff. That doesn't necessarily affect the structure, but roughly it's about 20%. We can build a building that's 25% more. That's significantly better seismic performance, and it might be 10, it might be 20% more expensive, but that's 10% more expensive on 20%
right
of
that's
your
what
construction cost. So it's like 2% more.
Right.
So can you imagine buying the Volvo and saying, you know what, the anti-lock brakes and the airbags, I'm not planning on getting in an accident, so can I save a couple bucks and take those out? And again, my only point is I appreciate the opportunity to have a conversation, have an informed client making informed decisions.
Right.
If they go bare minimum, man, it's like, great. That's what my license requires of me is the building code. Let's do that. It's efficient.
Very interesting. I wanted to ask, about designing different types of structures or using different structural systems. So wood versus steel versus concrete, and more from the perspective of like hiring an engineer. Like, how important is it to work with an engineer who has experience doing that specific type of structural material? Or, I mean, like you started off, you didn't know anything about wood construction and somehow it worked out. So, like, are those lines squishy, or do engineers specialize with types of construction?
It's a very good question, and the popular answer is, I want the engineer's already done it 20 times.
Yeah, sure.
And there's something to be said for that. On the other hand, how creative is that engineer going to be if they've already done it 20 times? Are they a cookie cutter?
Right.
100%.
Yeah.
So I actually, and that is the way that the industry tends to think. Fortunately or unfortunately, I'm the engineer who's always doing something he's never done before. So when it comes to solving, now at the same time, having touched all these different things, the reason why I could bring fluid viscous dampers to the house in Portola Valley is because I did them on the baseball stadium and I did them on a project at Genentech. So I knew, and having the master's degree from UC Berkeley in the seismic engineering, like when Anil Chopra, when we God, it's so funny, we're killing ourselves taking his notes because he writes so fast, and he's this old dude, he's about to retire, little Indian dude, he's short, and he's like, but literally the textbook that everybody in the country uses for structural dynamics, earthquake design of buildings is Anil Chopra's book. And finally, we're killing ourselves, and someone finds, it's like, dude, it's verbatim from the textbook. You don't need to write anything down. All he's doing is like, it's all, anyways. I could bring that to the table in a residential project because I've been in these different areas. I've been involved in baseball stadium, biotech lab, hospital, just regular office, like, hey, can we put stairs to go between here and then, we got both floors. Sure. Let's do a cool stair design. The knowing the right tools, knowing when to use a sophisticated analysis, when to just do a hand calc, that kind of engineering judgment, that's what I'm proud to bring to the table. The colleagues that I know of, that's what they do. My friend who was engineer of record of the Cal Memorial retrofit, the Hayward Fault, if you're not familiar, the Hayward Fault goes right through Cal Memorial Stadium. Mm-hmm. And half of that stadium is just built into the bank, and half of it is actually a building that's up above the ground. And they had to separate the two so that when the Hayward Fault, when that side of the stadium goes flying 15 feet that way. And I love teasing him because he's at the big firm and they've done it all, and like, he's the guy, right? And I'm like, so Renee, let me just get this straight. How many stadiums have you done? How many stadiums have you done and had an earthquake? Have a fault run to it? We're kind of having fun because it's like, at some point, you're a really good engineer, you're a really good seismic engineer, you're a really good communicator, you know when to bring the little hammer, you know when to bring the big hammer, and you know when to, hey, if you want to do a stadium with an earthquake fault running through it, I'll give you Renee's number, it's not me. So yeah, we do production housing, but yet we do this bespoke stuff where, we know that those windows, that $500,000 window system, we know that great big beam that's spanning 25 feet over, we know it can't deflect more than 1/4 of an inch. That's not code. Yeah. That's like the window guy saying the window's not going to work. The door, yes. The big bifold door, it's not going to work if that beam is sagging down. That's not code. That's like, what does it take to get this to work?
What is the most challenging thing about what you do, you think?
Jeez.
That's an easy one.
Yeah.
Or one of the most challenging things. Doesn't have to be the most.
I'm not sure if I need to go off script and say keeping my wife happy or keeping my kids in line.
That's a fair response.
Because this is easy compared to that. Just perhaps in this day and age, there's just so much information coming at us, so many different places. And as I have this whole conversation, I also, the Diamond Council of America recommends that you spend 2 months' salary on your engagement ring. I'm like, shit. And the Ice Cream Council recommends you eat a gallon of ice cream every night. Like, I kind of feel like a salesman, like just trying to sell something. But it's not. At the end of the day, my goal is not gold-plated structures. It's no surprise clients. And so perhaps the challenge is just like, hey, can we have 5 minutes?
Yeah.
And at that point, if you need another half hour, if you need another hour, if you want to like dig into the equation of motion and see why damping, as you do the integrals, is you go from sine to cosine and back to sine, and that's why stiffness and accelerations are on the same phase, and why damping is counter phase, and like we can do that too. But for the first 5 minutes, it's just like, what other engineered reality in your life? Hey, this airplane, oh, it's from the 1970s, but dude, like, it's good. Like, can I get on the new plane, please? So just that initial, just having and our first goal is obviously the architect, and then it's up to the architect. But then, the client's probably more interested in what kind of, marble they want to get for the kitchen.
Sure.
So how do we have that conversation? And again, what's fascinating to me is with such a tech-driven, it's not like we're in the fashion industry in the Bay Area. It's like, okay, fine. We're in the engineers are sort of like the heroes of the Bay Area, and yet it's still hard to get that. Like, no, I know you've got way more money than I do. It's not about money. Okay, you have that money because of a different thing, and that doesn't make you smart in this thing. And so just give me 5 minutes, and if I'm not onto something, fine, we'll do code minimum.
I think that's all very fascinating, and I like your response a lot to the previous question about having different experiences and how that is a benefit or a negative or a benefit, what that means for working with an engineer who has that range of possibilities. And honestly, that what you said is a theme that we've seen across different professions within the building scope. So we spoke with a contractor and they felt the same way. Like, all right, it's a benefit that we've done different things because we have these fresh perspectives that allow us to sometimes solve legitimate problems in a new way, or a way that you wouldn't typically expect, or allows them to stay loose, or whatever. I did have one question about process. For what kinds of structures are you guys doing 3D computer modeling versus, I don't know, just 2D CAD work and hand calculations? Like, how does that go for you?
Really good question. We are currently working on, back to the brick house. It's got a partial basement, and they want to lower the floor. It's probably got about 7 foot, and we want to drop the floor down to get 9-foot ceilings in that. And this is pretty common in a basement, but this is a really good example of it. You can design your basement walls just using a 2D, it's almost like a hand calc. And it's just a cantilever retaining wall calc. And the first time, that it was probably almost 10 years ago, the first time we were looking at a house was down in Los Altos. And it was a really big basement. It was a new basement under a house. And there was a lot, they actually had like 12-foot ceilings in the basement. And they had a lot of light wells. The bedrooms, you have a basement, it feels like a basement, but if you put some light wells in, for one, you can have the egress and actually call something a bedroom. And for two, you're just letting more natural light and air in. So they had a lot of these light wells. So we didn't really have a straight line retaining wall that's just, sitting there with the earth pressures. We had all these ins and outs, and we had done the line. We'd done just this simple hand calc, and here's the rebar for the wall, here's the rebar for the slab. And that doesn't take into account, anytime you have a retaining. So if you're looking at that line, but you have a wall going the other way, it's like, well, that kind of braces it, doesn't it?
Mm-hmm.
So I said to the contractor, I said, I have a feeling we can cut a lot of rebar. Or actually, the first thing I did is I said, what's your rebar number for the basement slab and wall? And, he said whatever it was, a couple $100,000 or something. I don't remember. I said, would it be worth me doing about $3,000 or $4,000 of 3D analysis to see if we can cut that by, a pretty substantial number? And we had a relationship where A, trusted me, like, might be onto something, and B, contractually, like, yeah, sure, go check it out.
Mm-hmm.
And we did, and we pulled 40% of the rebar
Wow.
out of that, where it was a direct, like, here's your bill for the ad service for $4,000 in engineering, and he went over to his rebar guy and dropped $50,000 in rebar.
Yeah.
So in terms of the engineering analysis, it's back to that. You should kind of know the answer.
Mm-hmm.
If you really do have a 2D phenomenon, fine, and use 2D analysis. But what are you missing in that 2D analysis? And is what you're missing there something essential, or is it something not essential? And is it, you can do the 2D analysis because it's conservative, or you can do it because it's not conservative and you're going to miss something. So we're just thoughtful and mindful about that. We love engineering, but we don't want to do it just for the sake of engineering. I say that there's times where it's important to know that pi is a number between 1 and 5.
Mm-hmm.
And there's a time where it's important to know that pi is 3.14159.267, whatever, right? And a good engineer will know the difference. They won't just go, 3.14159. That's stop, dude. Yeah. 1 and 5 is all I needed.
Right, right.
In terms of the drawing production, we have developed Revit capacity over the last couple of years and have a really strong Revit program. But again, you got to be careful, because we can spend a lot of time, particularly if the architect is still refining things and changing things. And if we get in there too early, mm-hmm. we can spend a lot of time changing things that don't, at the end, add value. So on the Revit, it's really important to communicate with the team when it's appropriate for us to get involved. Mm-hmm. On the other hand, the architect might say, I am going to change things a bunch, but part of why I'm going to change stuff is because of having your structure in the model, and I'd rather you do it than we do it. So yeah, and when we get there, send me the change order because I value that information. Okay, fine. Again, sure. No surprise clients. So there's times where things are kind of straightforward. If we might be doing a small remodel, and even if the architect is in Revit, it really doesn't make sense for us to make it complicated and do it in Revit. The coordination benefits are just really minimal. Yeah. Basic structure. Other times where things are a lot more interwoven. I've talked with architects who have gone to everything in Revit and then gone back because they're like the values just they're constantly chasing the model, and they didn't feel like they were really adding value for the complexity. And there's other architects who are doing everything in Revit.
It's interesting
on the residential side.
On the residential side, yeah, it's an interesting topic. That's probably a whole podcast in itself about Revit. And you're right. One of the dangers with it for you guys apparently, but definitely for us, even as more on the design side, of getting sucked into too much detail way too early on. And just as a brief as a side note, most of the instances where I've used Revit on projects, we don't go into Revit at the beginning. If we do, there's a technical guy who does that, but the design folks have to be loose and thinking about different things. We work in other 3D spaces, and eventually we'll basically recreate stuff in Revit because it creates this, as you said, chasing the model. You're always having to chase this model. It's like, why is this model determining how I work and what I'm doing every day? It's kind of silly. Last question for me was, I was curious to know what has been the most challenging structural project you've undertaken, or it could be even a portion of a project.
I'm going to answer with another sort of sidebar, and then maybe I'll come up with an actual project. Part of why I have grown a business is because at some point the project of the practice became really compelling to me, almost more so than the project of the project.
Mm-hmm.
So growing the practice is really fascinating. In terms of projects, one of them is certainly the house down in Portola Valley that we did the supplemental damping and did a real high seismic performance. We did San Francisco, going back to kind of the Northridge earthquake and seeing people dying, in an earthquake in apartment buildings. San Francisco was moving forward on the community action plan for seismic safety, and they were implementing a apartment, 5 units and greater, wood framed apartments, a retrofit mandate. And it was the first retrofit mandate since the brick buildings were required to be retrofitted. And I'm doing wood frame construction, mostly residential, but this is a really easy pivot. And so I ended up getting really involved with the building department and some committee work there, and the Structural Engineers Association Existing Buildings Committee, and helping them go from the law that was passed to the technical bulletin that the Structural Engineers Association had helped the building department put together, and some research work that had been done with a FEMA grant that developed a new methodology to look at these soft story buildings and not analyze the whole building, but just analyze that soft story, and helping the building department, helping the plan checkers understand how to interpret these rules and regulations, and helping write some further clarifications for the building department that ended up getting published and disseminated to the practicing engineers. We also did about 100 of those soft story retrofits.
Wow.
In terms of technical, I put, so one of the things they did over at Cal Memorial Stadium is they put a very sophisticated layers of membrane under the superstructure portion of the stadium, so that as the earthquake, as that first big jolt really slams, that the building can actually slide on that. And I was, again, really good friend of mine who was the engineer of record on that. And you've heard of Visqueen, right?
Mm-hmm.
Like you go down to Home Depot and you buy that plastic sheeting, and it's called Visqueen for some reason. I'm like, Renee, seriously, the best idea you could come up with is put the whole thing on Visqueen?
Yeah, just go down Home Depot and buy some.
I mean, dude, I could have come up with that. So it actually was way more sophisticated than that.
Sure.
There was no technical innovation here, but in terms of going back to what inspired me to really dig into structural engineering early on in my academic career and getting to serve the community in that way. And those buildings are bad buildings. Part of why that ordinance was passed is because there's such a critical vulnerability. 1989 gave us the reality that in that an earthquake that didn't cause strong ground shaking in the Bay Area, in San Francisco, look at how bad it was.
Right.
When the Hayward Fault goes right here, or when the San Andreas Fault goes right off of Ocean Beach, all of San Francisco is going to look like what the marina looked like in '89. All of San Francisco is going to look like that. And to know that I had a part as a professional I'm not a banker making deals and moving things from here to here. I'm not a lawyer fighting for this or arguing for that. I'm a structural engineer, and we as humans need food, water, shelter.
Mm-hmm.
Boom. So I love culture. My wife got me this jacket for my birthday, and I like it. I get compliments on it.
Looks good. Yeah.
I love good food and wine, but to know that it's like, when I'm hanging up the phone from my buddy that retired at 40, and he's got his big place, that it's like life's good. Life is really good. Proud to be a structural engineer.
That's great. I think that's a great note to end it on. Well, thank you so much for joining us on the show and have taken the time to chat with us. It was great.
It's been a pleasure.
Thank you, everybody, for listening to this episode. If you like what we're doing, then please support our show by leaving a review in the Apple Podcast app. You can also find us on YouTube, support us on there, support us on Spotify by subscribing. They don't have reviews yet, which is annoying a lot of podcasters, but you can subscribe, share, like, blah, blah, blah. It's all great. You can also look us up on our website, which is secondstudiopod.com. Reach out to us via any of the social medias. We're on all of them, mostly Instagram, really. And email, right? Which is hello@secondstudiopod.com.
We also have the hotline, 212.
212. This is in New York.
What is it?
Yeah, take a look.
213-222-6950.
You sure?
Let me check the board. Yes, that's right. You can send a text message, or you can call and it goes to voicemail directly, so you can leave us a note if you have any feedbacks, guest suggestions, any topic you want us to talk about, any personal advice maybe you might be looking for your career.
Mm-hmm.
We've done that a few times, and with the little experience and knowledge that we have, we're always happy to.
No, don't say that. Don't say that. Don't say the little. Don't little us.
We're more than happy to help you guys out as much as we can. And that's pretty much it. As far as the giveaway goes, a lot of you have submitted reviews on iTunes. So thank you very much for that. We're still waiting a few more days to make sure that anyone who sent a review would go through.
Yeah, so we're going to announce it next week, so make sure to tune in next week. And we'll announce it probably on social media as well, in case you decide to. What? Is that not accurate?
Just cut me off once again. Then people are like, oh, David talks too much. Well, no shit, really.
You gotta keep it going.
You gotta
keep it going. It's like a.
You talk too fast. It's like you're afraid people are going to steal words out of your mouth.
One foot in front of the other.
Gotta chill, man. Gotta chill. All right, people. Thanks for listening. Thanks for watching. Thanks for tuning in and all the reviews. We love you all very much, and can't wait to publish the next episode.
Yep. Talk soon. Bye.
Bye-bye.